Good afternoon, everyone. I'd like to thank you all for joining us today in our continuing education series. Today our featured topic is understanding OTDR trace analysis. My name is Jessica Petrohoy, and I'm the marketing coordinator at fiberoptic.com. Fiberoptic.com is a leading provider of fiber optic products, training, and rental equipment. We are pleased to present this topic to you today. As the growth of fiber optic networks continues, so do the requirements for testing and certifying the network. As network speeds move from 10 gig to 40 gig, 100 gig, and beyond, the need for testing these high-speed networks is critical. So choosing the right OTDR that will give you a complete picture of your fiber plant can be a challenge. There are hundreds of OTDRs from numerous suppliers with hundreds of options and configurations. Remember that our staff at fiberoptic.com is always here to discuss your current network and needs and can help you choose the proper OTDR based on your needs. So once you have your OTDR, you need to understand some common terminology related to testing, such as dead zones, reflectance, dynamic range, and types of events. So with us today to talk about OTDR traces is Terry Power. Terry is one of our senior instructors and a field technician with over 25 years in managing and testing networks. Terry will be discussing OTDR traces and helping you understand the results and hopefully some pointers along the way. Remember that our webinar series are recorded and available to you online at fiberoptics.com/webinar. When Terry has finished, we will take questions from the GoToMeeting chat box at the bottom of the screen for a question and answer session. So thank you again for joining us today, and at this time I will turn the presentation over to Terry.
And good afternoon, everyone. Again, this is Terry Power. I'm senior instructor here at the Fiber School and one of our testing engineers. I started working cable television in 1987 and have pretty much grown up through fiber optics through cable TV and moved over into data. And again, I have been doing this for about 25 years. What we're going to talk about today is an OTDR trace and how to understand what it is you're looking at. And all right, so we're going to have a brief introduction about the OTDR, talk about what it is. We're going to talk about how the OTDR actually creates the trace. We're going to talk about what an OTDR measures, what parameters we have control over, and then how to read the trace itself. Then we'll have a little bit of wrap-up and then a question and answer session at the end. Remember to put your questions in the chat box in the GoToMeeting, and we'll get to those questions after the presentation. Okay, so an OTDR is an optical time domain reflectometer. It is used to characterize the fiber. It's a snapshot, if you will, of the fiber and the events and losses that are taking place over distance at the very moment that you're doing the testing. It's used typically from one end of the span or segment. It calculates the loss of the signal. It shows the distance to the event and helps us for troubleshooting in that regard. Again, it's used for testing and troubleshooting, and it measures optical return loss. The trace that we're going to be talking about and looking at is a graphical representation of the losses that occur over given distances on the fiber in that moment. It is a snapshot in time. And of course, any changes that you make, even in real time, can affect the trace. So how does the OTDR create a trace? All right, basically a controller is going to send a signal down to the laser, and it's going to start a clock. Now you'll notice the clock and the pulse that you'll see animated here in a moment are running concurrently. So the laser is going to fire a pulse, and it is going to go down the fiber under test. The clock is now ticking, and the return, whether it's from backscatter, ends of line, or whatever, is going to come back in, go through the detector, and then the detector is going to send a signal up to the controller saying stop the clock. And then we're going to look at the elapsed time and the amount of reflection, and from that, the OTDR is going to start plotting points. Now you'll notice, and I'm going to use my pointer here, the return signal level is on our vertical axis, and our horizontal axis is going to be distance. What happens is we get a backscatter point plotted based on the time it took for the pulse to go out and the backscatter to return. That's how it determines the distance. The amount of received signal is then used to plot the points, and you will see that there's a little loss, a little more loss, and over distance you're going to have some amount of loss per kilometer. Then these points are plotted, and then the OTDR will connect the dots, and all we end up seeing is the connecting line. Now that is a basic OTDR trace of a bare piece of fiber. Now, of course, we're going to have to add the end face and the launch event. This is the connector at the OTDR, and at the end of line, we're going to have some kind of reflective event where we have the air glass boundary, and then from there it will fall off into noise because the light is just escaping into the air at that point. Now, if we add a splice into the fiber, you will notice that there's going to be some amount of loss. You look at the backscatter level before the event, the backscatter level after the event. The difference between the two of them is the calculated loss of the event itself. Then if we put in a reflective event, we have a very similar situation. The peak of the reflection is compared to the backscatter level before it, telling us the amount of reflectance. And then the backscatter level before and after is compared, and that gives us the loss of the event itself. In its basic form, that is an OTDR trace. Now, what do we actually measure? A lot of people think that an OTDR measures loss and measures distance. The short truth of it is that an optical time domain reflectometer measures time and measures reflectance. That's it. That's the whole magic, is it measures time and reflectance. Based on the speed of light in the medium, it calculates distance, and based on the backscatter level, the reflected light before and after the event, it calculates the loss. That's why a power meter and light source will always be the most accurate means of determining loss. But it gives you the overall loss of the span, whereas an OTDR allows us to look at the calculated loss of any single event. Now, returning to our previous drawing, now you can start to see that this measured reflectance and the calculated distance based on the time is how we plot each of these points. We look at the splice and we're looking at the reflection from the backscatter before, the reflection from the backscatter in front of, and that difference is the calculated splice loss. So we're measuring the reflectance coming back, and that gives us this line. We're calculating distance, and we're calculating loss. Same thing with the reflectance at a reflective event. We're measuring reflectance, the amount of light returning, and again, that's plotted over time or over distance, which is determined by the time it takes to go out and back. The OTDR sends out that pulse of light, and it starts the clock, as we saw in that earlier animation. The OTDR has to know the correct speed of light in the fiber. And if nobody's told you guys yet, the speed of light is not a constant. When we think of the speed of light, we typically think of the speed of light in a theoretical vacuum, or the speed of light in space, or whatever. That's not what we deal with in glass. That's not what we deal with in the atmosphere. The speed of light within our atmosphere is different than the speed of light in a vacuum. And it is certainly different than the speed of light in the fiber. So we use something called the index of refraction. And the index of refraction is a formula. It's a very simple formula, C over N, C being the speed of light and N being the speed of light in the medium. And by comparing the two and using that ratio, we come up with a number like 1.46, 1.48, that is the speed of light in the medium, and the OTDR takes that information along with the time out and back and calculates the distance. The trick is we got to make sure that's entered accurately. We've got to go to the manufacturer. We've got to make sure that we have the correct index of refraction, because if we tell the computer the wrong speed, it's going to tell us the wrong place. You know, the old saying about computers, garbage in, garbage out. The OTDR is a fancy computer. And if we lie to it, it's going to lie back to us. So for total distance accuracy, you've got to make sure that you get with the manufacturer and determine the IOR for that particular piece of glass that you're working with. Now here's the basic formula, and those of you that remember back to junior high school, when, you know, a train left Chicago going this many miles an hour and it traveled for this long, how far did it go? Distance equals velocity times time. Pretty straightforward, actually. And it's something we learned in junior high school. Now, in this case, in this formula, distance equals time times the speed of light in a vacuum over 2 times the index of refraction. And if you remember a second ago, I said the index of refraction formula was C over N, C being the speed of light in a vacuum and N being the speed of light in the medium. If we do a little algebra and take that aside, we actually have time times C over N, which is our index of refraction, the velocity of light. And then, of course, we divide that by 2 because we're taking a trip out and a trip back. So this distance here is divided by the time divided by 2. And it's really that straightforward. There's no real magic here. It's just simple junior high school math. But if we give it the wrong information, we're sure going to get wrong answers. And there we go. All right, now it's letting me get there. Okay, one last thing to recognize about the distances that we're talking about is there are three distances that we talk about in our calculation. We have the shortest distance is going to be our physical length, whether it's our trench footage or strand footage, whatever it is. In this example that we're looking at here, we might as well look at this individual standing out there scratching his head. I don't know if he dropped his shovel or what, but anyway, this is the guy standing out there in the field. Here's our central office, and they're about 120 kilometers apart geographically. That strand footage or trench footage or any combination thereof, that's our shortest distance. And that's what we want to know. But that's not what the OTDR is going to tell us. We've got to remember that we've got splice enclosures and slack loops and all of these kind of things in between. So if we accommodate all of this, we'll have a sheath footage, which will, of course, be 10 to 15% longer than our geographical distance. So we might have as much as another 20 kilometers of sheath footage. So just with the sheath, we may be up to 140 kilometers. And then if you take into account the helix factor, which is the twisting and untwisting of the buffer tubes so that we can strengthen the cable, as it goes down the line, that could be another 5%. So now we're looking at 140, another seven or so kilometers. So we're looking at close to 150 kilometers of optical length. And all we're really trying to look at is this. So having good drawings, having some kind of good asset management so that you keep up with where all of your slack is and your helix factor, that's going to give you the correlation between the length of the glass, which is what the OTDR is going to shoot, and the length on the ground, an actual location on the ground. So again, in this example, we might be shooting 147 or 150 kilometers with the OTDR. Then we've got to take out the helix factor and all of this slack to get back to 120K on the ground. So those are just some of the things that you want to be aware of and some of the limitations of the OTDR distance measurements. You have to know what it is you're looking at. Now, what parameters can we control? All right, let's see. We can control the distance range. That's typically called just the range setting on the OTDR. We can set our pulse width. That's going to be determined by the distance, and we're going to dig into each of these in turn. Acquisition time. Some brands refer to the number of averages. But the idea is how long, how many averages, how many data points do you collect to get you the smoothest trace possible. Resolution is going to be how often does it sample a data point, whether it's every 10 meters or every 1 meter, every 16 meters. Each different brand is going to have its own numbering system for the resolution. But you're going to be looking at that, and we're going to look at how that matters to the distance to event measurements. And of course, IOR we've already talked about. You tell it the wrong speed, it's going to give you the wrong distance. And all of these, we're going to look at how they affect the trace and how they're going to affect your ability to analyze the information that you're receiving. Now, distance range. This one's pretty straightforward. As you can see in this example, the range on the OTDR, if it is set too short, you're not going to see the entire cable. You want to make sure that your range is set. You would like for this marker here to be 25% or more past the end of line. Sometimes there's valuable information down in that noise floor. That's stuff that we can talk about in a classroom environment that's a little beyond the scope of this webinar. But we will definitely discuss that in the classroom sometime. So when some of you guys come to the testing classes, we'll talk more about the information in the noise floor and how it can be how that can be utilized. But the point here is that we want to make sure that the range is set far enough out here that we see the beginning and the ending of the entire fiber. Now, pulse width. Pulse width and dead zone and dynamic range all kind of intermingle and do this dance where we're going to be looking at different ways that it affects the trace. And this is possibly the most important setting that you will set on your OTDR. And you got to look at it this way. A 10 nanosecond pulse, which is typically your second shortest pulse width, will give you 1 meter of light. I describe it like this. Picture a water hose hooked up to a faucet, and you're getting ready to wash the car. You turn on the faucet, and then you turn it back off. Maybe you turn it on for 1 second, turn it back off. You're going to have a certain distance of that hose with water in it. And it's going to flow down to the end of the hose. If you turn that water faucet on for 10 seconds and turn it back off, you're going to have 10 times as much water or 10 times as much hose full of water. The pulse width does the same thing with the fiber. You turn on the light switch for 10 nanoseconds, and you have a 1 meter wide pulse of light traveling down the fiber. That means that at any given point on that fiber, there's 1 meter of light. And that pulse travels down and then travels back. You multiply that by 10 and go up to 100 nanoseconds, and you get, just like you would expect, 10 times as much light. Not in intensity, but 10 times as long a pulse, 10 meters of light. Picture that. That's 33 feet of light. There's a lot of our head ends that we don't have 33 feet between the patch panel and the outdoors. So with a 100 nanosecond pulse, you're already not seeing light, seeing any events inside the inside your central office or head end. And on long runs, where you have to turn your pulse width up to like 10,000 nanoseconds or 10 microseconds, that is a kilometer of light. That is over half a mile of light traveling down the glass, reflecting and coming back. Now the thing about the dead zone is that very simply, when that light hits a reflective event, such as an end of line, more appropriately a set of connectors in the field or in the central office, or it hits a mechanical splice in the field, a crossover box, fiber distribution hub, whatever you've got going on with connectors and mechanical splices. When that big pulse of light has got a hard reflection and it's bouncing back, you've got however long your pulse is, you're blind to any of the backscatter for that distance. So if you've got a 10-meter pulse of light hitting a reflective event, and then it's coming back at you for that entire 10 meters, the detector can't see anything except that reflection. So the period after your reflective event is the dead zone, and it's based totally on your pulse width. And as you can see on these drawings, the blue trace has a very narrow pulse width. And you can see the spike on the trace, you don't even tell that it's wide. It's just a spike straight up and straight down. On the green trace, you've got a medium set, and you can see a little bit of width right here. And then on the red line, you'll see a very long pulse width, and you see the width of the reflective event. The width of that reflective event is your dead zone, because I can't see what's going on in here. And that has an effect on my ability to analyze the trace. The problem is, we would, of course, say, well, if I need all that detail, I can go with a really short pulse width, like this, like on the blue line. The problem is that also affects your dynamic range. And if you go to a really narrow pulse width, you've got a really low launch level, and you don't quite always make it to the end. Now we're down here in the noise floor, and we don't even see the end of line correctly. And you'll notice this splice event at, about 20 and some change miles is gone. We don't even know it's there. So we can turn up our pulse width to make sure we get to the end of the line nice and clean and smooth, but we get these big wide dead zones. So the correct answer is to find that middle ground. I generally aim for, in this region at the end of the line, I want somewhere right around dot 2 of noise from peak to peak. That allows me to get to the end of line with enough data or with enough smoothness that I don't lose an event like this. But it gives me as small a pulse width as possible, so I'm not creating these huge dead zones. Now, sometimes on really long runs, we have no choice. We're going to have those big dead zones. But we try to mitigate those by looking for that dot 2 of noise and keep our pulse width as small as we can and our end of line as smooth as we can, and then we dance. We dance the dance. There's always a balancing act. I call it dancing. I've got a colleague that talks about walking the tightrope. You fall off to one side, you got too small a pulse width, and you don't see the end of the line. You fall off in the other direction, and you got a huge dead zone, and you don't see some events. So we're always walking that tightrope or dancing the dance. Now, dynamic range, we've been talking about that as well. The higher our pulse width, the higher our launch level is going to be. And we've got to make sure that depending on the loss of the cable, whether we're shooting at 1310 with .35 dB of attenuation or at 1550 where we've got .2, we've got to look at how many splices, how long and far we're going. We need to make sure that this end of line stays above the noise floor. And we do that by turning up our pulse width. So that's where dynamic range comes into it, is in setting up the proper pulse width. Okay. And here's just another example of that injection level. Almost every OTDR is going to have some kind of bar here. The slide and our engineer calls it the injection level indicator. I typically call it the launch bar. It's just a colored bar on the side that tells me that this is where I should see my trace come out. So if I see my trace come out in that launch bar, then I know I've got a good connection here. If I see it come out down here and kind of roll and then start, that means I've got a dirty connector at my launch. But in this case, we're also talking about mainly the difference between the launch indicator and our noise is our dynamic range. And that can be set by the pulse width, as we've already mentioned, or the wavelength, as I talked about earlier. The loss per kilometer at 1550 is about .22, which will give us more longer dynamic range. Because we got less loss per kilometer, we can go about a third again further before we have the loss down into the noise floor. All right, measurement range. We talked about this on that very first slide. The measurement range is going to indicate how much we actually look at. We're telling it, in this case, I'm going to look at 20 kilometers. Now, if the trace kept going past there, that would mean that the fiber was longer than 20 kilometers. And this one's set up pretty nicely because it's just about 25% longer than the end of line. And here we can see some of the events down in the noise. And this gives us a really nice, clean trace, proper length, proper dynamic range. We've got a good launch indicator. Our pulses aren't too wide. That's just a really nice looking, easy to read trace that shows us what's going on with our fiber in the field. All right, dead zone. Dead zone is specified as a distance. When we were looking at that, you could see the width of the trace. Now, if we remember that that horizontal axis is distance, you can very quickly see that that distance correlation exists. There's a certain period of distance that we cannot see, and that goes along with the pulse width. It determines how close to the OTDR you can detect a splice, how close together two reflective events can be measured for loss. I do want to specify that here. As long as we can see the peaks, we can tell the reflectance based on the initial backscatter level. So the reflectance of the second and subsequent reflections may not be totally accurate. But we certainly can't tell the loss of them if they're within that dead zone, and we'll look at some pictures in a minute. The attenuation dead zone is how close together a reflective and non-reflective event can be measured. If you've got a wide enough pulse, you might have a splice that's actually hidden inside that dead zone. And if you narrow it down, you'll see that there's another event there. If you have a wide enough pulse width, the loss of both will be calculated together, and the loss of your reflective event may actually be the loss of two events. And again, always remember that dead zone is directly related to pulse width. The larger the pulse width, the larger the dead zone. There's no if. There's no all or other times or any kind of, it's always. This one's one of those very few hard, fast rules in the world. Dead zone is directly related to pulse width. It always will be, and there's nothing we can do about it. Now here we're looking at the attenuation dead zone. depending on the width of this pulse and where it returns to the backscatter level, because remember we need backscatter before and backscatter after to accurately calculate the loss. Now here it looks like we've got a splice event, but we don't look like we made it all the way back out of that dead zone. We've not fully recovered, so this very easily, the computer on board could very easily see this as a single reflective event with this much loss, from this backscatter level to this one. And it could very easily show that as a single event with a high loss, when in fact it's a reflective event and then a non-reflective event following it. So pulse width matters when we're trying to see those details. But then we got to get to the end of line. But we want to see the details, but you got to get to the end of line and you see the dance, the constant balancing act. Now here's to what we typically refer to as camel humps. These are two reflective events that have become merged because of the pulse width. And we can see the loss from here to here. And we can see the amount of loss for the pair of events. A lot of OTDRs will show you a symbol on the events table. Look, it's a sigma for summation. And it'll tell you, in this case, it would be 1 of 2 and 2 of 2. With that sigma off to the side to say that this is the summation of the total event. It would give you the total loss. It would give you individual reflectances based on this backscatter level, because that's the only backscatter level it has to look at. So this reflectance may be slightly inaccurate because it's using this backscatter. If there's any loss, the backscatter could actually be here, and this reflectance could be reported as low because it's looking at this as our only backscatter to compare it to. And this is the event dead zone. How far or how close together can two reflective events be and still measure accurately the individual events? Now, noise. We talked about noise a minute ago. The thing to remember is that noise is not coming from the light. Noise is not inherently on the glass. The noise in the trace actually comes from the OTDR. We've got detectors, amplifiers, signal treatment circuits, all kinds of electronics on board that are causing the noise. We just want to make sure that we launch high enough that we get out of the noise so that we get a nice clean trace. This just looks like a real short acquisition time on this trace because it looks high enough it ought to be smooth. So I'm thinking that's like 5 seconds of acquisition or something small like that. Now, acquisition time. Just like the pulse width can smooth out the trace, acquisition time, the number of data points, the number of averages, how long we look at it, can smooth it out. Now here we've got a very small acquisition time, and we don't have the detail out at the end. Here we've got just the right amount. It's a smooth trace around dot 2. Here at our end of line, we can see all of our events. The pulse width is narrow. The acquisition time is in that sweet spot, so we're not going too quickly and getting noise, but we're not wasting time turning it up and testing for 3 minutes just to try to smooth out the trace a little bit. That is a complete waste of time. And if you're doing construction splicing and testing, if you got to count do 144 count, and you add even a minute a trace, a minute a fiber, and say you're shooting at 2 wavelengths, that's 2 minutes per test times 144. So you've already added 266 minutes to your testing time. And, you know, I'm not real good at math, but that sounds like it's something really close to 4.5 hours. 4.5 extra hours to smooth out the trace a little bit more? Yeah, I'd probably just change the pulse width setting and do it with a 30-second test and get on with life. So again, here's another place where you're balancing. If you're shooting 3 or 4 fibers and you want to wait for it, well, you know, a couple of minutes is no big deal. And maybe that gives you a chance to use one smaller setting on the pulse width. But if you're doing a lot of fibers, you're going to find that sweet spot, and you're going to go for like 30-second tests and get on with it. Because that's still hours. I mean, that's 144 count, even at a minute per wavelength, you're looking at the better part of a day just to do that testing. So you've got to look at your needs and dance the dance. And I wish I could tell you that I have some pat answers and say, oh yeah, if you're shooting this distance, you should go with this set of parameters. It doesn't work like that. It doesn't work like that in the real world. You've got to play with it in the field, and that's why we're doing this webinar, so that you can see the parameters, understand what they are, so that you can go out in the field and have a little more confidence tinkering, because that's the way you're going to learn it, is to get in the field and tinker with the settings. Now, resolution. This is your dots per distance on how close together the data points are. As we were talking earlier, the lower resolution, which is your highest number, your highest distance, is what you want to go with, because it is much faster and it is a vastly smaller trace. That file size can matter. You start saving a whole lot of traces, you're going to have a whole lot of data taken up on whatever storage device. Now, the flip side of that, we talked about the pros, the cons, is that there is a slight degradation in your measurement distance accuracy. But if you know where your splices are, and you're off by 5 or 6 or 7 meters on your OTDR trace, is that really the end of the world? Now, if you're troubleshooting and you're trying to find that end of line, and you know it's between 2 intersections in a city block, you may want the most accuracy you can get. Again, it depends on your needs. That's why there are no, you're doing this and this and this, so set these parameters kind of charts. They don't exist because I don't know what your needs are. So I can't give you those kind of answers. I can tell you that your best bet is to start with the lowest resolution. In this example, if we're offered 32 kilometers / 2 meters, or 32 kilometers for our range at 16 meters, I'm going to start with that 16-meter resolution. That will give me a trace that is 8 times faster and about 1/8 the size when I go to store it, because I'm taking 1/8 the number of data points, is really what it comes down to. That's another simple math problem. If I need that accuracy and I turn down to a dot every 2 meters, I'm going to take 8 times more measurements. It's going to take me 8 times longer, and it's going to take up 8 times as much data in my storage. That's the short answer, is that you always want to go with the lowest resolution possible for all of those reasons. Now let's look at some real-world examples of that and see how much effect that really has. Now here we've got a long spacing. We've got 10 meters between data points. So each of these lines is a data point 10 meters apart. Okay, so we've got a splice here, and the actual location is right here. This is where it's going to show on the OTDR. That's where it's going to show the event, because that's where it begins to see that fall off at our backscatter level. So here's our backscatter. Here's our backscatter. This is the amount of loss, but it's going to see the event begin wherever the last data point was before the event. So in this example, it looks like we're maybe off by 7 meters, so about 20 feet. We're off in this regard. Now the next one we can look, sure, we can go down to that 3 meters, and 3 meters between, and our measured splice point and our actual splice point are much closer together, but we now have a file that's 3 times larger and takes 3 times as long to acquire. Again, if you're doing 1 fiber, 2 fibers, no big deal. If you're doing 144 fibers, it makes a difference. So you've got to determine these parameters based on your needs and what it is you're doing in your plant. Some other parameters that we mentioned, IOR, and yes, I do mention that a lot because that's one of the biggest things I see people do, is they'll have the wrong IOR set, and they're out there, 50 meters away in the dark with a flashlight trying to find somebody's fence post. Which one's the new fence post that they drove through our fiber. When accuracy matters, this is something that we can always get right. Backscatter coefficient is going to affect how our trace looks, and will determine the amount of compensation for the backscatter reflections. Wavelength, we've already talked about how there's a certain differences in the traces between 1310 and 1550. And then also if we shoot 1625, we can use multiple wavelengths to look for bends, macro bends, which are causing loss. And we'll dig into that in just a few minutes as well. All right, so now that we've got some of the backgrounds and understand some of the parameters and what we can control, let's look at a few traces. All right, reading the trace, we're going to look at reflective events. We're going to look at non-reflective events. We're going to look at launch and end-of-line events, some anomalies, gainers and ghosts are the 2 anomalies that we'll discuss, and we're going to talk about launch and landing box. Now, the non-reflective events are just simple drops in the trace. There's no spike, there's no reflection, it just goes from one backscatter level to another. This can be caused by a splice, a fusion splice, or by a macro bend. And we've got a slide coming up to explain that. Then the reflective events have this spike where you can see the hard reflection from an air glass boundary. Those can occur from a mated pair of connectors, a mechanical splice, or from a discontinuity. Maybe the fiber is actually broken inside the sheet but still holding together. You might see something like this. Now, as I mentioned earlier, our launch event is reflective. There's a connector that hooks up to the OTDR and goes to your patch panel. At the end of the line, the glass simply stops somewhere, and that end of line is where the glass stops, that air glass boundary, and it is typically a larger than average pulse because the light's not going any further. And then from there, you'll fall off into the noise. Okay, so a non-reflective event is a slight drop in the trace that we showed you. It's caused by a fusion splice or a macro bend. Fusion splices will have essentially the same loss per wavelength. So it doesn't matter if it's 1310, 1550, 1625. If the loss is pretty close to the same on all three wavelengths, you can anticipate that's a splice. Macro bends will have higher losses at higher wavelengths. I have seen traces where 1310 went straight through. 1550 showed me some loss at a location, and then 1625 just fell off into noise. 1625 is very susceptible to bending. And that's why a lot of the construction testing that we do behind splicers and construction people, when we're called out to do that kind of testing, is we will shoot 1550 and 1625 so that we can see where the bends are occurring, so that when someone decides they're going to use the entire spectrum with wavelength division multiplexing, they know that there's not any problems with bends that will show up later down the road. Reflective events, that's that spike followed by a dip. It is a mechanical splice or a mated pair of connectors. And in Fresnel reflection, I put this in here because sometimes you'll hear reflective events, sometimes you'll hear someone talk about a Fresnel reflection. Truth is, they're the same. They're just simply, Fresnel reflection is the more, I don't know, not necessarily the more correct, but it's, I guess, the fancier term, for lack of a better word. And Fresnel is individual in the 1800s that wrote most of the theories about light wave propagation that we know today. And all of that gave us the cause to name something after him. So Fresnel reflection is honoring that discoverer or that scientist. And then the event dead zones that we've already talked about. Anywhere it says behind, I say after. Well, that was a question as to which way is behind and after, but the distance, the blind spot to the right of the reflective event is the dead zone that we've already talked about. All right. So measuring a fusion splice loss, there's no back reflection, so it's just going to be simply the dip in the trace. It is usually measured, while we only need to get to one side of the OTDR, or of the span for the OTDR to work. Very often when we're doing our final testing, we will want to look at it bidirectionally, because sometimes subtle differences in the backscatter level will give us more or less loss in one direction or the other. And taking this bidirectionally and averaging it will give us the most accurate loss calculation. Now, this also brings us to the gainer. The gainer is one of the anomalies that we can see. Actually, it's the more common of the two anomalies. And what happens is the backscatter coefficient on one piece of glass is greater than the other. The OTDR just suddenly sees more reflection. Remember, all we're doing is measuring reflectance. So if it sees more reflection from more backscatter, it's going to see it as a gain. Of course, when you shoot that from the other direction bidirectionally, it's going to have a huge loss because it's going to be going from a lot of reflection to a lot less reflection. The way to accurately determine this is to take the loss from A to B with the gainer, then take the loss from B to A, add them together, divide by 2, and once those have averaged out, you have the accurate loss calculation for that gainer. And the gainer will typically be demonstrated or show up on your events table as a negative loss, which looks kind of funny when you see it the first time because loss figures are in positives. When you have a gainer, it shows up as a negative loss. Now, a ghost is a different kind of anomaly. This is an echo. And back in the old days, you might have had an OTDR with insufficient delay between laser firings and the pulse is too close together. That doesn't happen a lot now with the modern contemporary OTDRs. What you normally have nowadays is an echo. It is simply a dirty enough connector that is causing a high enough reflection that it's bouncing back to the launch connector with enough force to make the trip again. That's it. It's an echo. There are always multiples of the distance to that highly reflective event that caused them because it's seeing the same event twice. Let that sink in for a second. And a ghost is seeing the highly reflective event that caused it. It's showing it to me twice. That's it. That's the whole mystery of a ghost on an OTDR trace. It will have no loss because it doesn't exist. It's fiction. It's an echo. And it will ride on the OTDR trace with zero loss. And that will usually be the OTDR's first clue. And it will typically, any reflective event that has very, very low loss or no loss, it will set a flag to tell you to take a look at this because this might be a ghost. Now, again, what happens is the light makes the trip out, hits the reflective event, makes the trip back. Well, if it's coming back hard enough, it might make the trip the second time and go out and then back. Here's where it shows me the first event, which is real. And after this red line goes back and out again, or out and back again, it gives me this event here, which you can see demonstrated by the red line. And you'll notice it's exactly the same distance, and it has no loss. And typically, the reflection itself is going to be slightly smaller because it's made the trip twice. So it's going to have loss from making that trip twice. It is always a multiple. Now, it says on here, reduce reflections by changing the range settings. Yeah, if you turn down the power, you might turn down the amount of light that makes it back for that. Maybe doesn't have enough to make the second trip. Use a shorter pulse width. That'll turn your power down also. Use index matching gel. Try to reduce the amount of reflection here. I'm going to tell you that all three of those are wonderful ideas after you clean the connector, because contamination right here is going to be the biggest bulk of the reason that you have this out here. If this connector's clean and has minimized reflectance, this ain't going to happen. So all this is wonderful news after you try cleaning it first. Because usually when you clean it, the ghost goes away. All right, launch cables. We are running out of time, so I'm going to wrap this up now. Launch cables. Now, I've been saying throughout this webinar that losses are calculated by looking at the backscatter level before and the backscatter level after an event. If I need to test my patch panel connector, if I just plug straight into it, I've got this launch event right here. I don't have backscatter before it, so I can see the backscatter after. I don't know how much loss I have. A launch box simply gives me backscatter before my launch event. It places a piece of straight fiber to give me backscatter between my OTDR and my patch panel. That's it. It's not a pulse suppressor. It's not a dead zone eliminator or any of that voodoo sounding stuff. It's simply a straight piece of glass that allows me to measure the loss of my patch panel. If I don't have a serious need to measure that loss, I don't have a serious need for a launch cable or a launch box. Now, here we have a little bit of a demonstration. Here's our launch connector, our patch panel. We have nothing back here to compare it to. So it tells me that it doesn't know the loss. On the other hand, if I put in a 500-meter launch box in this example, then I can see backscatter before, backscatter after. I can get an accurate loss measurement and a more accurate reflectance measurement. And then, of course, I've got the unable to measure the beginning of this, but I don't care about that. And then the OTDR will typically let me set my span, my beginning of span, and I can set that to here and set my 0 to my patch panel. And that gets everything set up nice and neat so that I'm seeing my distances as correct according to my patch panel. All right, so wrapping up and in conclusion, some of the parameters that have to be set correctly: index of refraction, backscatter coefficient, wavelength, range, resolution, number of averages, and pulse width. Remember that dynamic range and resolution and pulse width is all going to affect your dead zones and how well you can see the entire span and noise at the end, and all of that's going to play together. Here's another quick example of a narrow pulse width. We see our two events starting to separate, but we get noise out here. Sometimes it'll get so much noise, in fact, that the OTDR will see the end of span before you get to the end of the span. Here we've gotten a wide enough pulse width that we can see all the way to the end. There's still a little noise, but we can still see all the detail. But these two events that are really close together might be a co-location site or a head end where you go through a couple of patch panels before you go outside. But here they're merged together. Sometimes you might want to take a short shot and a long shot so that you see this end very clearly or see this end very clearly, or and a little of both. All right, the required data to perform an OTDR test and their impact on the measurements. So index of refraction and pulse width is going to have an effect on your distance accuracy. Getting that pulse width and range of distance is going to have an effect on your distance range itself, and as well as the dead zones with your pulse width. Spatial resolution all comes into play here. Acquisition time and wavelength and pulse width are going to determine how much noise you have at the end of the line and your small events detection capability. And it's also going to have some effect on your event measurement distance accuracy, and then your helix factor is going to certainly play into your distance accuracy when you're looking for sheath footage versus optical footage. And so now I'm going to go to the chat room and look for questions. And let's see. We have a question here. How will the end-of-line reflection differ between a cut, manufacturer end, FDP termination as opposed to the reflection of a break? I get the general idea of what you're asking. Okay. The end of line can look different. A nice cleaved connector end of line with a UPC connector is going to have the biggest spike. That flat, smooth, beautiful cleaved end is going to give it the best opportunity to bounce back as hard as possible. An APC connector is going to simply roll off. It will have very little to no end spike. It'll just simply roll off into the noise. And breaks, whether it's from stress, depending on how straight it is, how jagged it is, how much of an angle, it's going to be somewhere in between those two extremes. And I hope that answers your question, but yeah, that's very good. First time I shot into an APC connector and I saw it just roll off into the noise, I was a little surprised. And I had never seen an APC connector at the other end. This was some years ago, of course, but the first time I saw it, it was a little surprising. And breaks will sometimes not have as much of a spike because if it's a really jagged edge, it's going to scatter the light rather than reflect it hard. And let's see, I've got time for one more question. And this one was emailed into, oh, wait a minute. Looks like we've got another one. How do I measure ORL with an OTDR? Okay, that's a little bit outside the scope of the trace analysis, but real quickly, when you go to your measure tab, whatever brand of OTDR you have, there's some capacity to determine what you're measuring. I'm most familiar with Expo gear, but the newer Pro OTDRs also have the ability to set some cursors. And you simply go to the Measure tab and select ORL, set your cursors on either side of your span, make sure you get that beginning and end reflection, and the ORL is the measure of all reflections between the two cursor points. Now, on the other hand, if you're using some kind of automated power meter and light source transceivers, those will typically give you ORL at that point as well. So I hope that answers your question, Justin, and thanks for being with us. And, of course, we are way out of time. I've gone about 10 minutes over, and already people are standing at the door watching me. So we're going to go ahead and wrap it up now. If you have additional questions, please feel free to email those questions to training@fiberoptic.com. And is this webinar available for review on your website? It will be available sometime around 1 week from now. All of our webinars are recorded, and they are put up in the archives on the website typically about a week after we do the presentation. So thanks to everyone for being with us. We appreciate your participation, and we look forward to your input on additional subjects and topics that you would like to see. In fact, if you have additional topic ideas, you can also email those to training@fiberoptic.com and put in their webinar suggestions. We'd love to have your input because we do these things for you guys, not for ourselves. So thanks a lot for being with us, and have a great day.